today we're going to talk about exponential and logarithmic equations. We're not going to do the inequalities part, but we're going to do the equations part. So we're going to solve exponential equations. There's two different ways it can happen. All depends on the equation we're looking at. And then we're going to solve logarithmic equations. Now the first thing is that we're going to do is we're going to look at utilizing our calculator. All right? Because I want to make sure you get the right answer. Okay? This tends to be kind of hard, okay, for some people. And so I want to make sure at least you can get to the answer, and then we'll work on the method for getting there algebraically. All right. All right. So here is an exponential equation, because we have something raised to a power equals something else raised to a power. So the first thing we're going to do is we're going to look at it with our calculator first. All right? So put the left side in y1 and the right side in y2. So 9 raised to the power of 8 minus x, and 27 raised to the power of x minus 3. Is that right? Okay. All right. Okay. Zoom 6. And we're looking to see where these two intersect. So we can see from the graph there that they are not going to intersect from where we can see it happening anyways. So it's going to happen somewhere in here though, right? Between 0 and 10. Okay. The nice thing about our calculator is that we could find the answer right now, but I want to at least see it, so I need to do what with my window? Okay, so I need to go up, all right, which means we're changing what? Okay, y max, all right. Okay, so we'll try 100. See if that helps us. Oops. All right. Let's try 100, and nope, doesn't help us, so we need to go higher than that. Okay, so we'll try 1,000, see if that helps us. And yep, looks like 1,000. I can see where it's intersecting right here. All right, so what do I do now? Not zoom trace. Second trace. And number 5, intersection. So, and then we're just going to hit enter 3 times. It only happens once in my picture, so I just need to enter 3 times. Once for the first curve, once for the second curve, and once for guess. So the answer here is x equals 5. All right, so we know the answer. All right, so x equals 5. In all of these problems we do today, whether they're exponential equations or whether they're logarithmic equations, you can solve all of them by doing that. Left side y1, right side y2, find the intersection point. Okay. All right, so now let's look at it, doing it algebraically. So the first thing is we want to look to see if we can make the bases the same. All right, so we want to rewrite each side with the same base. In other words, okay, can I write 9 and 27 with the same base, but obviously the powers are different? Okay, so what number raised to a power equals 9 and raised to a different power equals 27? 3 does. Okay, 3 does, right? 3 squared is 9, and 3 cubed is 27. All right, so I'm going to rewrite these. 3 to the second, and 3 to the third. Okay, what do I do now?
Solve for the exponents.
Eventually we're going to, but we have to do something before we just solve for the exponents. Okay, we're going to multiply. All right, we're going to multiply 2 times 8 minus x, and multiply this 3 times x minus 3. So we get 3 to the 16 minus 2x power on the left side, and 3 to the 3x minus 9 on the right-hand side. Now, okay, we now have the bases are the same. Well, if the bases are the same, and this is a true statement, what must be true about the exponents?
The same too.
Okay, they must be the same too, or they must be equal. So now I'm going to write them as 16 minus 2x equals 3x minus 9, and we're going to solve that equation. So when we can, we want to make the bases the same, so then I can just set the exponents equal to each other and solve. We'll have a linear or quadratic equation. Okay. So we add 2x to both sides. All right, we get the x's together. Then add 9. So we get 25 equals 5x. And we know that 5 times 5 is 9, or 25. Right. Okay. So when we can make the bases the same, we're going to do that first of all, and then we can set the exponents equal to each other. Okay. All right, letter B. Okay, so find the answer to this graphically. Okay, find the answer to this with your calculator first. All right, so the first thing, we find the answer. All right, we got that. X is approximately 2.16. Now the question is, can I make the bases the same here? Can I raise the number to a power and get 4 and the number to a power and get 5? Okay, no, we can't. All right. So if I can't make the bases the same,
Don't have to do anything else.
oops, cannot make the bases the same, then we're going to take the log of both sides. All right, so that means we're going to have the log of 4 to the x minus 1 power equals the log of 5. So now we're going to use that power rule that we've done, and we're going to take that x minus 1, because when it's in this form here, 4 to the x minus 1 equals 5, we have no way to get the x minus 1 out of the exponent from anything we've done before. But if we take the log of both sides, now I can use the properties of logarithms, which say I can take the exponent and I can move it to the front. So now it's out of the exponent and it becomes a linear equation. All right. So like I said, it gets a little bit tricky, a little tough. Okay. So we have x minus 1 times the log of 4 equals the log of 5. Right? So I'm trying to get x by itself. That's always been our goal. Okay. So what's one thing that we could do right now? Type into your calculator. We already did that. Got 2.16. All right. Okay.
Look at the X.
We could, all right, we already know the answer, so, all right. We have two options here, okay? We could distribute the x and the negative 1, all right? Or we could get rid of the log of 4, all right? Since it's multiplication, I can get rid of the log of 4 by dividing by it. So I'm going to divide by the log of 4. All right, so I'm going to end up with a decimal number here. So I go to my calculator. Log of 4. Close the parenthesis. Divide, log of 5 divided by log of 4. So we get approximately 1.16. So x minus 1 is approximately 1.16. Then we add 1 to both sides. So x is approximately 2.16. So there's two different things we're looking at when we're solving exponential equations. One, can I make the bases the same? Right? If I can, then I'm going to do that, and then I can just set the exponents equal to each other. If I can't make the bases the same, then I'm going to do the log of both sides and solve for x that way, because then I can take the exponent and I can move it to the front. All right? So I want you to do A and B here.
Bye-bye.
All right, 1A, you're going to be able to make the bases the same, so work on that. B, you're not going to be able to, so you're going to have to take the log of both sides. Okay. All right, suppose a bacteria culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1 million?
Oh.
A bacteria culture doubles in size every hour. So that means that we have f of x equals 1 times 2 to the power of x. Okay, this is our exponential equation. We have one thing, we start with one thing, it doubles every hour, so I multiply it by 2 to the power of x. Okay. So if I started with 1 after 1 hour, after 1 hour I have 2, after 2 hours I have 4, 3 hours I have 8, and so on. We want to know, when is it going to be bigger than 1 million? All right, so we have two options here. One, we graph it. All right? Or, which is actually, because the length of time it would take you to graph it, you can actually do it faster probably with doing the log of 1 million equals the log of 2 to the power of x. Because we just bring the x to the front, divide by the log of 2. Hayden's got the squeaky chair.
That's some WD-40 in my truck after long.
Of course you do.
What are you trying to say, Hayden? Take this stuff apart.
Catch me outside, how about that? My WD-40.
How about that?
Spreading your eyes. You able to blink perfectly. What?
All right, so we solve it. So like I said, in this situation, find the answer. Okay? If the only way you can find the answer is by graphing it, then graph it. All right? So 2 to the power of x and 1 million. All right? So I know my window's got to be big enough to get to 1 million here for y max. So 1, 2, 1, 2, 3. All right, graph. All right, looks like I'm going to need to go a little farther to the right. So let's go 30.
Good, you failed.
What are you
talking about?
Yep, there we go.
Different answer.
All right.
How'd you get 34? I got 19.
So second trace, number 5, 1, 2, 3. All right, so it gives us 19.9. So in approximately 20
Hours.
20 hours, the amount of bacteria will reach 1 million. And if I do the log of 1 million divided by the log of 2, I will also get 19.93. So x is approximately 19.9 hours. And then you would need to make a statement that says, in approximately 20 hours, the bacteria will exceed 1 million. All right, so you have to make sure on those questions that you write a sentence for me. All right? Okay? All right, so let's see if you can find this answer. All right, okay, so we're going to solve the logarithmic equations now. All right, so exponential equations, we either get the base the same or we take a log of both sides. Logarithmic equations, we want to solve them so we have a single logarithm so we can change it to exponential. All right? We want to get simplified to a single logarithm and then we can change the exponential form. So this is why it's really important that you can go back and forth from exponential form to logarithmic form and so on. Because basically those exponential problems, you could change those to logarithmic form and solve them. Right? Or in the logarithmic equations, we can change them to exponential and solve them. All right? So, first of all, go to your y equals.
Oh, yeah.
All right? Put the left side in y1, the right side in y2, find the answer. Left side y1, right side y2, find the answer, first of all. Just make sure we can get there. Log base 6, so was it 2x minus 1? And we want to know, when does that equal negative 1? Zoom 6. Second trace, number 5. Now, you have to be careful because there's nothing here, right? Right? So we have to scroll over till we find a y value before I can actually do this in my calculator. All right? So you can't, it won't do anything if it just says y equals nothing. So enter, there's my first curve, there's my second curve, and here's my answer. All right? 0.58333. All right, is our answer. All right, so now, we have a single logarithm, we're going to change it to exponential form. Well, what does that mean? That means here's the base, right? So it becomes the base for this exponent. So when I change it to exponential form, we get 2x minus 1 equals 6 to the negative first power. Right? All we're doing is changing it from logarithmic form to exponential form. Now I have a linear equation. So we add 1 to both sides, and then divide by 2. Six to the power of negative 1 plus 1. All right, 1.35, and divide by 2. So we get x is approximately 6.68. So all we're going to be doing is using basically the properties of logarithms, using the properties of exponents, solving these equations. Okay, letter B. Now I know you can do it with your calculator. Let's just work on finding it algebraically. Okay, the log base 4 of 100 minus log base 4 of x plus 1 equals 1. Okay. So the first thing we want to do is simplify it so it's a single logarithm. So here we have a minus sign between two logarithms. What does that minus sign tell us to do? Divide. So we have the log of 100 over x plus 1, all right, base 4, is equal to 1. All right, if you need parentheses here to help you, then put parentheses there. Okay, log base 4 of 100 over x plus 1 equals 1. Okay, now I've written it as a single logarithm, change it to exponential form. So that means that 100 over x plus 1 equals 4 to the first power. All right, so here's my base is 4, my exponent is 1, equals 100 over x plus 1. All right, what do I do to solve this equation then?
You gotta multiply.
Close. Okay, we have to multiply by x plus 1. All right, we got to get that whole thing out of the denominator. So we have 100 equals 4x plus 4. Or you could just leave it like that and divide by 4 first. Either way. Okay. So then we subtract 4 and divide by 4. So x equals 100 minus 4 is 96, and 96 divided by 4 is 24. All right, and if you stuck that in your calculator, you would get 24.
Can you just look at it and say it's 24 though? 100 divided by 4 would be 25, so obviously 24 plus 1 is 25.
What? That's pretty slick right there.
Okay?
Makes sense.
Brain cells from that one.
Jared, you say you lost too many?
Yep.
All right, here's another one.
That or you don't have any.
All right, letter C.
Change this crap into exponential.
Any other crap you'd like to say?
All right, now, do this one in your calculator first. Do that in your calculator. What? 0.5? 25, okay. All right, so we change it to exponential. So we get x to the 4th equals 5 to the power of 8. So how do I get rid of this 4 here then? When it's x to the 4th. So we want to get rid of this, we have to do the 4th root. Okay? The 4th root. All right? It's like square root, but it's the 4th root. So on our calculator then, when you go to math, number 5, you can put in whatever root you want. So we put in number 5, and the root is 4, 4th root of 5 to the power of 8. And we get 25.
So I'm going to do like x equals 25, is that what it is?
So x equals 25.
More school, more problems. More math, more problems.
All right, one more. Last one. Okay, what is a single logarithm? What does plus tell us to do?
Multiply.
All right, multiply. So we've got the log base 12 of x squared plus x equals 1. All right, we're multiplying x times x plus 1. That gives us x squared plus x.
Big sigh.
All right, change it to logarithmic form, or to exponential then. So x squared plus x equals 12 to the first power. Okay. Now, we have x squared, which means it's a quadratic, which means we've got to get it equal to 0. So we have to subtract 12. So we get x squared plus x minus 12 equals 0. All right? And so my next step would be to do what then? Factor it if we can. And this we can. We get x plus 4 and x minus 3. All right, so x equals negative 4 or positive 3. Now, you have to check your answer. And in this situation, negative 4 does not work. All right? The reason is, if you remember when we first were doing the logarithms, we talked about domain for logarithms. And the domain for a logarithm has to be greater than 0. So if we put negative 4 up here, I can't take the logarithm of a negative number, so negative 4 doesn't work. My only answer would be x equals 3. So that's what we call an extraneous solution. It's one that we get. It doesn't work when we go and check it then. All right, and if you put this in if you solve this with your calculator, you would see that there's only one place where those lines are going to intersect, okay? And that's going to be at 3. So, exponential equations. If we can make the bases the same, we will, so we can get the exponents equal to each other and solve. If we can't make the bases the same, we take the log of both sides. Logarithmic equations. Okay? Get them into a single logarithm, change the exponential form, and then they become a nice linear or quadratic equation that you can solve.